So, our next presenter works as a sysadmin and systems programmer, and most of his work involves in building highly concurrent data processing pipelines. Today he'll be talking about developing highly concurrent data processing pipelines. Please welcome Daniel Bryan.
Alright, so first of all I wanted to apologise. Since my talk's opinionated, I was going to use all these emoji to illustrate my point, but this Mac, actually at the last minute, I found out doesn't have emoji fonts, so you can get a spoiler there of some of the emoji I was planning to use, like skull. The reason for my talk, there have been other talks today about concurrent programming. The talk earlier on functional programming is actually relevant to mine as well. So I want to convince people that they should care about writing concurrent code. One of the essays I want to reference is called "The Free Lunch is Over." So for a lot of problems, it's no longer possible to actually solve them by writing code that operates in a single-threaded fashion. And also that it's not too bad and that you don't need to worry about it too much. And that involves countering some myths about how difficult it is and so on. So first though, a note, almost everything I'm going to talk about you can avoid until you get to a certain level of complexity and still manage to take advantage of what the operating system can essentially. Of the systems I've built that are heavily concurrent were initially basically bash pipelines, and you realize you need to, at some point you need to make something run on 2 cores or whatever, and to a pretty great extent you can do that by using things like split and GNU parallel. And then if you need to run on multiple hosts, you can even use features that GNU parallel has that can pipe data over SSH or something like that. And you can actually get pretty far. And if it gets hard to manage or you're not too good with bash, you can start to use Python or Perl to manage processes and stuff like that without actually having to get into hardcore threaded programming. But eventually it gets too complex. Or you need to manage some shared state between them, and for whatever reason you don't want to use a database. So a little bit of terminology. Most people will probably understand this. Parallelism refers to doing something physically, more than one thing physically at once. So if you have a multi-core processor, you have code essentially running at the same time on both of those cores. Concurrency just refers to doing that logically. So it can just be an abstraction. Concurrent code can be logically doing more than one thing at a time, but running on a single core. I think it refreshed. So why is concurrency important? This is just a quote from one of the articles I'm referencing, referring to the fact that basically we have more or less hit, some people think we've hit the peak in the clock speed that can be improved on a given core. Desktop computers are basically getting faster by adding more cores. Supercomputers are using things like GPUs, which are massively parallel, and so on. And that was actually targeted at C++ programmers, who obviously wouldn't be very happy about that. So, as I said, commodity desktops have a lot of cores. There are phones that have 4 cores, which is insane. Anyone who has a gaming system has a GPU with thousands of cores. It is hard to write code targeting them. I haven't really researched it, but it seems intimidating. A lot of people, particularly people who work in science and medicine, even on trivial problems will have something like, they'll be trying to work on something they need to hack together on their workstation laptop, and it'll be, a 600 gigabyte data set or something like that. And the kind of turnaround you need on projects like that, if you have such little resources, you need to take full advantage of the computing that you do have there. Everything can or should be MapReduced, which means even if you've got some huge expensive cluster, you don't always want to actually express your problem that way. So if you have an unforgiving environment where you can't introduce latency by doing something like sending the data over the network, you need to take advantage of what you can do on a single host. I read in one of the abstracts for later in the conference, one of the people from ANU who's lecturing said they're soon getting a supercomputer with 60K Sandy Bridge cores. And apparently it runs Linux. So presumably you could write applications that target that. I don't know if it runs one instance, but one of the reasons that parallelism is important Obviously, I've covered this, people are working with huge amounts of data. I should be explaining what these emoji are. That's a graph going up on sensors. Here, on the left, it's the emoji for money bags, so it's a bag with $1 on it, and on the right, there's a graph going down, because it's like, the enterprise is bad or something. So they have lots of data, and interestingly, if you talk to people who are doing what they call big data, they're all using Linux for everything. There's no question about it. No one does something like these hardcore, massive Hadoop implementation deployments on anything but Linux, even when they're accessing it through Excel. And yeah, so the thing is, something like Hadoop or whatever you want to call more, or proprietary solutions, they're very operationally expensive. They have huge amounts of network contention, often particularly with HDFS, and they're pretty over-engineered, and the complexity doesn't really hide, even in one part of the team. Like, the developers have to worry about how the Hadoop architecture works and things like that. So my approach is really to think about concurrency abstractions. So I'm more interested in what you can do at the level of what the language actually offers you, rather than what a library can do. So I'm not interested in things like this, which you can do with C. I really don't think anyone should be using something like the pthread API with what we have now. So a few myths I want to counter. Number one, that the cloud, or that this idea of purely horizontal scalability can solve certain problems. Number two, that it's too difficult for most programmers to start approaching things in a concurrent way. And number three, that it requires really complicated programming constructs to actually do it. So first, though, I want to just say, regarding functional programming, people would have picked this up from earlier today. These are properties which generally you would put into an API. So if you're designing something like a REST HTTP API, you want it to have these properties. You want data that goes into it to act transactionally. So usually there'll be a structured database backend that offers that. And Rich Hickey, in one of the talks where he introduced Clojure, basically said, why do we do this when we design our APIs, but not when we design how our programs actually work internally, when obviously these seem like, well, this is subjective, but some of these things seem like intrinsically good properties to have. That's fine. So the cloud. Why won't the cloud save us? I can't really remember what these are. I think they might be... Oh, that's right. These are both just up arrows as well. So things like, people say, well, you can just, don't worry about how scalable your application server is. Just package it in Python or whatever, and you can run it on Google App Engine or on Cloud Foundry, which is open source. And you don't need to worry about provisioning and things like that. Not every programming model works with that, and not every development approach in terms of how you actually iterate while you're developing works with that. So it can be hard to integrate with other existing servers you have. If you're working in this weird application container, you can't create arbitrary connections and things like that. And obviously, if you want to actually do something interesting, so you're collecting data in this web app or in this contained app, it implies that you have this database as a service where you can just magically store it all, and that will never have any consistency or performance issues. And there's no such thing. So the second myth is that it's too difficult. So to step back, to illustrate my point, I've been programming for about 2 years, writing concurrent code for 9 months. I've talked about that, but I consider myself a reasonably average programmer, so I spend a lot of time debugging. This was meant to be a new line. My bugs per line of code is astounding, but despite that, basically I started doing programming for work and went directly to doing concurrent programming without really a bridge of experience writing simple imperative programs. And actually, most of those projects are intuitively easier for me than writing straightforward code that simply manipulates business code sequentially. So I think it's really an issue of how people have been educated to program. So this is just, in case people are curious, languages which I have used to write concurrent code. So the way people are being self-taught now is actually frequently by learning JavaScript, because people are interested in learning how to make a website or something. And if you talk to young people who have done JavaScript, they won't understand what a class is, but they'll understand something like a continuation or a callback, which is quite amazing when you consider that there are arguments saying that asynchronous or concurrent programming is fundamentally difficult. So why has this happened? Partly because of the APIs that people have used traditionally, like pthreads, and partly just because as soon as you do concurrent programming, you intrinsically have this problem of data races, and you need to model your data in a way that can deal with concurrency. And the third myth, so the third myth is that there's intrinsic complexity as soon as you make things concurrent. And to counter that, I think there's two things you need to talk about. First of all, how are people actually making their code run concurrently? And secondly, how are they actually managing that so that they can access data safely? So for that first issue of how you actually make your code run concurrently, I'm going to talk about Node.js as a kind of case study in what I think is a bit of misinformation about this whole issue. And these two emoji are both the pile of poo emoji. So Node.js is very popular. I don't want to rag on people who are interested in it, and it gets a huge amount of attention. Like when Microsoft launched their kind of App Engine equivalent service, they made a big deal of the fact that you can host Node.js on it, which I actually found surprising at the time. And Yahoo use it for lots of things. A lot of companies use it, including a lot of open source projects. Here's some code that you might have in some JavaScript environment that isn't, or it could be Node, but let's say it's not, where you need to look up 3 APIs and then return it or whatever. So you call your API, each instruction takes a while because it's making a web request or requesting something from a database or whatever. And each of those happens, takes a certain amount of time. This is the total amount of time before your function returns. That's fine. So in Node.js, instead, here's what you get. So this is what a naive Node.js programmer would do. You call, get some data. Once you get that response, you go, great, I want to get my next thing. And you pass it a callback, which gets called when you get your next response. So in that callback, you go, great, I've got that. Then you say, well, I'm going to need this as well. So in the callback for that, you go, great, I've got that. And when you've got all of them, you can call the final callback, which actually returns the data to the caller, and then the caller has to have set up a callback on that to deal with the data. So this is to solve the supposed problem in here that while you're doing each of these things, in a single threaded process, nothing else can be happening. No other requests can be accepted or whatever. So here you solve that problem. But of course, the time until the callback is called is still 35 milliseconds. Now, as I said, this is naive, but I've read a huge number of Node.js applications, the source of lots of Node.js applications and libraries, and this is extremely common. They say, oh, this stops you from blocking, so everything will be faster. Actually, in terms of the response time of this handler, it's identical. It'd be slightly slower because you're yielding to a scheduler every time you do this, and you've got this event loop running. And also, note that the complexity of this, while I was hacking it together, meant that I put the wrong attribute here for Yahoo. And I don't think you can blame anyone for a mistake like that when your code goes from this to this. So what's wrong with it? The benefit is, so say you've got /dot and you just have a huge volume of requests, you don't have to worry about it as much as you otherwise might, because every time you call this and you send it the callback and then you yield, something else can happen. But yeah, how do you debug this? You're going to have to run a test framework which has an event loop, right? How do you manage that? Do you want to write those unit tests? I don't. How do you signal errors? So this is a more realistic version. Every time a callback gets its result, it gets a possible error value. This is purely conventional in Node, and a lot of libraries don't actually do it properly, or they'll do it as the last value, even though you have variable number of arguments in JavaScript. So you have to test whether the error variable has been set to non-null. If so, you call a special error callback that returns the error value. Otherwise, you continue doing your work. And so this is what you end up getting to do 3 things, to make 3 calls to API or database or something. And of course, since here I accidentally put the allocation of t to the body property of this res object before I tested the error thing, if there was an error, this might have been null, and then I throw an exception. And again, the convolutedness of this whole event, callback-driven approach makes errors like this more or less inevitable. So you want to get around that. You don't want to have these trees. So every call, instead, every single Node.js programmer writes their own little library, like callback manager. And you can say, well, I want to add tasks to this thing. Some of these tasks have a dependency on the other task. This is how I want you to aggregate this data, so I want you to reduce or map the output of all of these callbacks, and you tell it to start, and it'll eventually call your final callback. And there are like thousands of these libraries, and every project is using a different one. So to get around it, you end up, to figure out complexity like this, you basically have to, in your own head, figure out a dependency graph of everything you want to do, embed it in a data structure or something like that that can manage the callback tree for you, pick one of those, and still hope you get it right. So no one should be doing this, obviously. So what are people really trying to do when they take this approach? Well, basically, they want to avoid this problem where sequentially you're saying, get us a connection from this socket and then handle it. So usually in C, the solution would be, excuse the fact that I don't really know C very well, but you'd say, well, here are the file descriptors that I'm monitoring to have data available, so I'll wait till there's data available on them and return the file descriptor that has data ready to be read or written to, and then you handle that. It's still kind of blocking if this is single-threaded, but it's a lot better. So most event loops are basically just an abstraction on top of these system calls. Node.js is no different. As far as I know, libuv uses them. So why can't we let the language do these things for us? Why is there a dichotomy between whether we do something in serial or in parallel in this way? Most of us write code in high-level languages. I'd like to make the point that Haskell is an extremely high-level language, even though people think of it as this kind of hardcore thing. It's actually a higher-level language than anything that almost anyone writes in terms of pure definitions. And yeah, I think unless we're writing code where performance is absolutely crucial in a way that would impact other applications, we shouldn't really be worrying about things like this. So, quick example, some Go code. This is a function which does the same thing as that JavaScript code, but the point is that what it does, to achieve it, it spawns 3 Go routines, which are essentially a green thread. So they run on real threads, but you can have lots of them and they're cheap. So you say, here's my counter for how many results I've gotten, which will initialize to 0 by default. Spawn 3 green threads that'll do their work in the background somewhere. Go will make sure that in any given thread, so even if this is single-threaded and you do this blocking call, it only looks like a blocking call in your code, and the language runtime is actually will take this green thread off the real thread and throw it on its own event loop. But the point is you don't have to think about that. You make some function calls, you do some ad hoc thing like set up a account, have sent something on the channel that says I'm done, and then you've got your data ready and you can return. So this is a lot simpler, in my opinion at least. Bit more complicated in Go. To be fair to the JavaScript thing, some error handling. Doesn't really matter though. The point is that if you're just worried about solving what Node.js is trying to solve in the naive case of not blocking other routines, you can just write it imperatively, and the scheduler will make sure that whenever you make this blocking call, this function gets taken off its real thread, and the runtime makes sure that something else gets to do some work. So yeah, the point. So we know that we want threads to do this, but threads are expensive and complicated, and there's also a mismatch because if you really want to architect your program nicely, you want to say, well, this is a unit of computation I have. I want to call this a thread, but then you suddenly have to start worrying about, well, what's the cost of the stack for this thread? What's the cost of the OS doing the scheduling, and so on. So I think the Go solution is a lot nicer. If all you're worried about is the fact that you have a lot of IO-bound work, don't write your own ad hoc framework for managing callback trees, which is what every single Node.js programmer does. If there's not a good library for doing something like this in the language you're working in, you're using the wrong language, at least for now, until it matures. And the same really applies to some of what people try to do with Twisted, some of what people try to do with Event Machine in Ruby, although those have their own real applications. So I think what we really want is cheap green threads where you have your code can essentially pretend that it's sequential, that you have semantics that say, well, here's my function, these are the things it does, it returns this value, and the runtime, or the VM, or the Linux kernel scheduler handle that for you. Languages that do this really well are, I know that Erlang and Go do it really well. I'm told that Haskell does it really well. But as a stopgap, if you're using an event-driven framework or something like that, you can do something like use continuations, which is what Twisted does. So, I think I'm misusing the word continuations, but essentially, instead of sending a callback, you get a promise, and you can pass that around and do things like it. So it was done in Python because you can't pass anonymous functions like you can in JavaScript, but if you get a promise object back, you can kind of build nice libraries that encapsulate them, and that's the reason there are good conventions in Twisted for saying, here's a list of things that I want to get done, I want you to monitor them all till they're done and then do this. Whereas since you don't have you don't have this constraint in JavaScript, you end up just everything's ad hoc. And yeah, Twisted essentially even now lets you do it inline, so you can write code that essentially does what Go does, where you can write what looks like sequential code, and it'll yield when you're going to do a blocking operation. Obviously, since it's Python, it's still going to be single-threaded, but it's better. Yeah. So the last thing I want to cover is how you make concurrent code safe. So it's really how do you safely access and transform data that you want to pass between multiple routines, or that you want to actually, over time, share and transform in a more complex way between routines. You have the issue of synchronization. If you have a background process running and you need to know that you want to do some work while it's running, and you need to know that it's done before you return, and you don't have access to its return value, what you really want is something like a queue or a channel that, that can allow you to know that it's done. And by default in Go, if you use its primitive for sending data between threads, you get synchronization by default. And a lot of other languages offer the same thing. So things with really simple, straightforward, if you do this, your threads will be synchronized when you do a read, or when you make some call or something like that. So this call will block until another thread is synchronized. But in Go, it's a language feature. And in Clojure, and you can do this quite well as well. So the real problem is if you have shared memory. So this is the main reason people say that writing concurrent code in C is hard. You've got concurrency in something like C, where a function is essentially, C is not a single-threaded language if you use the threading API, but in terms of how a block of code in C runs, it's single-threaded and it's imperative. Now, even if you only have one core, you still need to worry about the fact that if you've got multiple threads running, they can be rescheduled and you'll have a data race, basically, and your program can crash or be wrong. So the obvious way to manage that in C and traditionally is to use mutexes. You have a real program with complexity, you're going to need granularity of locking. So say I've got a 500 gigabyte memory map file, and I want to say I want to safely transform these 100 bytes in here where this data is stored. Well, you don't want to take a lock on the file. So you say, oh, it's all right, I'll have a data structure which has locks that apply to different subsets of byte offsets within this memory mapped file. So okay, are these just plain locks? Are they locks where you can have many readers but one writer? What byte offsets do you choose? It starts to get to the point that, again, it's all ad hoc, and it's not nice. So instead, you might say, I'm going to have apply some structure to how I share my data. I'm just making up this term, structured sharing. It's not a thing, but you need to think about, first of all, if you're going to pass data around within your program, are you sharing it by value? So you're sending a value like primitive into some function, or bytes over a pipe, or are you sending a pointer to some data structure that could be accessed from multiple places at a given time, or are you sending access to a socket which theoretically could be written to or read from by multiple processes, So when you do structured sharing, you essentially conventionally use some kind of data structure or operator or other primitive that allows you to do thread-safe access to some data. However, if you're sharing things by value or just sending some bytes around, you don't need to worry about this. So wherever possible, if you can just send, an array by value, or if you can send bytes to someone on a pipe, you don't have to worry about a race condition. You just have to worry about how you're going to resolve, potentially conflicting writes or potentially conflicting data down the line. But at least you won't have, if I send data to someone, I want to know that I can still use it for something else. I don't want to worry that if I pass some struct or dict to to a library function, that it's going to mess with it, like trying to sort in place or, I don't know, whatever. You really need strong semantics about whether you're passing something by value or by pointer. Is probably one of the biggest things to figure out when you're trying to share data. Are you trying to modify a global? In that case, an alternative to something like highly granular locking would be to have something like a broker thread which owns the data and serializes access to it. So this is obviously what you do if you've got a database. So with Postgres replication, as far as I understand it, it's common to have many readers, so many things where you can make queries that are a select or something like that, but only one database that's a writer or a transactor. And you can do the same in your own programs. You can, instead of just directly looking something up on a data structure or directly writing to it, you have to go via some dedicated channel or function call that handles this for you. As the previous speaker said, 0MQ is really nice. Sending JSON or protocol buffers over that, or just over a pipe or something like that, is a really good way to kind of architect things in this way, even if your language doesn't really support this. And you can even have in-process ZMQ buffers or queues or whatever, so where all the data will actually stay in your process and it's just a way to manage things that happen within your program. You can have structured sharing of immutable data, which is really the nicest thing you could possibly do. There is a cost of copying the data. So if you share an immutable value, but then the person who gets it needs to do something with it, they're going to have to copy that data. However, in languages like Clojure, you have these things called persistent data structures, where you can have an immutable data structure, but to, say a hash tree, sorry, a hash map, but to modify a key, the value at a key, or to add a new key to it, which requires creating a copy because it's immutable, can still be a very cheap operation because they share struct, essentially. And that's really something you only want to do if you have a language like Clojure where your basic data structures can offer those kind of persistent semantics. This was not supposed to be on this slide. Go and Rust are supposed to be here. So it's common in Go especially to just, the Go developers would tell you to manage thread safety, send data on a channel rather than reading it from a global data structure. But of course, in practice, you read Go programs, they're all sending pointers around on channels everywhere. So, and that's idiomatic as well. That's not misuse. That's how it's done. So you're on your own again. So of course, I have a lot of Go software where I do most of my types or classes, which is what they really almost are, have copy methods, and I do a defensive copy before sending it on certain channels, rather than spend hours debugging. Yeah, sharing immutable data on a channel that has strongly defined semantics and processes that don't actually share, essentially, the abstraction is they don't share any memory with the other green threads or processes, as they're called in Erlang. But the last model for managing the way you can share data is to use, this is obviously not an exclusive list, but to use software transactional memory, which is how Clojure, really it's Clojure's killer feature. You can do it in GCC with Transaction Atomic. I don't know anything that uses this, but essentially, it does what a database transaction does for you. So like how with the database transaction, you'll wrap it in begin and commit, or transforming like these three things, and you want to make sure that no one else sees the intermediate copies, or that no one, if no one changes this after you've read from this or whatever. You can do all that inside basically a transactional block. The language handles it for you. It just works. You just have to make sure you have tests, because obviously if your transaction fails, what the language does is it auto-retries. So to make sure you don't just get infinitely auto-retried, you will need to do something like have a test in your transaction that can cancel it in the case that someone else has transformed the data, so that someone else's transaction got in before you. But this is pretty simple stuff. People deal with this, in a lot of web apps when they write, when they code to the database API. So I think people can deal with that, and using a language that offers that to you really gives you a lot of power and means you don't have to worry as much. You can just not worry about it, how you share data. Okay, so yeah, you can punt on it. Sometimes, I don't know, I have programs that should have race conditions, but it's never really a problem. Sometimes that's easier than deciding what to do about, the deadlocks you'd get if you started having locking everywhere. Remember, all these things I've talked about, they all interoperate with all these things, like whether you've got p-threads or event loops and thread pools or whatever, but none of these really imply the things you actually need to do the work to manage sharing data and making your program be correct while it's concurrent. So since these are such low-level constructs, and the real work comes in deciding what to do when you share a mutable value, I think people should just bite the bullet and use a language that makes this decision for you. And thanks to Chris, not this one, who suggested that the Minicomp speakers finish with this this question of whether anyone wants to start a fight. And these emoji are like a flexing arm, both of them.